All right, so our lesson today is going to have two parts to it. The first thing we're going to talk about are rotations and how to complete them. So we've talked about translations, which is just shifting something left, right, up, or down. We've talked about reflection, so we're kind of flipping something or reflecting it either over an axis or some other line of symmetry. And now we're going to talk about rotations, which is the last of our rigid motions. And so you probably should write down that rotations are a rigid motion, and rotations are just going to rotate or kind of twist things. So rotations are going to change the orientation of a figure. So a lot of this I'm going to show you in class tomorrow just because it's easier to show you in person, but some things that I want you to take notes of. So what we see here, this is it's kind of some old computer programming, but this is what it would look like if we used a computer program to rotate an image. So some things that I want to point out to you. Notice in this image down here for B, these two figures are congruent. They still look to be the same size. We haven't changed the shape or anything, but I want to show you what happens when you rotate something. So first of all, you rotate around a point, and that point is called the center of rotation. And notice if I map B to that point and B prime, what that does is that shows me two things. One, the distance that the figure is away from the point of rotation is not going to change, so that is congruent. All right, even if I did A to A, right, those would still be congruent distances there. But also, if we draw that out, we can see what the how the rotation is measured. So rotation is measured in two ways. One, it's measured in its direction. So are we going clockwise or counterclockwise? So this, if I go from B to B prime, this is an example of counterclockwise. And then it's also measured in terms of degrees, and that is kind of like the degree that is made between these new images, or sorry, the image and the pre-image with the point of rotation. So for example, this appears to be like a 90-degree counterclockwise rotation. I could draw these same lines or segments rather, connecting like C and C prime or A and A prime, and all of them would have that same idea of congruence and the same measurement of 90 degrees, that same angle of rotation. All right, so at the top here is just some more of that vocabulary. If you didn't get that down from the last slide, make sure you get the vocabulary down, and just the same two things about how rotations are measured. Okay, so here are some shortcuts about how to do rotations in a coordinate plane. And these are true when we are rotating about the origin. So we'll find out how the rules change tomorrow if it's not about the origin. And what all that means is that our center of rotation is right here at the origin. So you all know how I feel about rules. I don't really tend to like the rules, but sometimes they make things easier. So I'm going to show you this way, and we'll use this in class tomorrow, but I'm also going to show you a way in class tomorrow that's kind of more of a hands-on visual way to work these problems out. So a few things that I want to point out. 90 degrees, a 90-degree rotation, because a whole circle is 360, 90 degrees is going to be like 1/4 of that. So it's nice that our coordinate plane is already set up into 4 different quadrants. So let's look at if we have a 90-degree rotation. So if my original image here is at 4, +4, +1, if I rotate this 90 degrees, notice that my point goes to -1, 4, which should give you an example of where they're getting this rule. See that the y became negative and moved to the x spot, and the x is simply moving into the y spot. All right, if I do 180-degree rotation, so I'm going to take this blue dot, if I start it here, and I rotate 90, and then another 90, notice I'm going to be in the 3rd quadrant now. So now, as a 180-degree rotation, this is going to end up at the point, and you can just see it on the graph, -4, -1. All right, if we do our next point, that's 270. So I'm going to start here, 90, 180, 270. That's going to land me at, let's see, that's 1 and -4. So notice my coordinate rule is still applying that they've given me. And then my last point, 360, that is not what I wanted to do. My last point, 360, I guess I'll just have to draw that one, would end us back exactly where we started because we'd go all the way around. So that one is going to end at the same point, which is still 4, 1. All right, and just to show you one more time what that center of rotation is looking like, I'll do this with the 270. If we connect, right, our points back to our center of rotation, this is 270 degrees in a counterclockwise direction when I open that up. You may notice also that 270 counterclockwise is the same as 90 degrees clockwise. All right, so that's all that we have for rotations. So we'll work on this a little bit more tomorrow. Let's look at what our next skill is for today. All right, so this next lesson is talking about symmetry. And what we're going to do here is we're going to combine a few different things. We're going to talk about lines of symmetry. So if we look at our essential question up here, lines of symmetry, which should make you think about reflections. And then rotational symmetry, which should make you think about rotations. So we've got some definitions here about symmetry and lines of symmetry, if you want to pause the video and copy those down. And a line of symmetry is really just the same as your line of reflection. So our goal will be how many lines of symmetry can we draw, or can we come up with lines of symmetry for different figures. So an example, they've given us a rectangle here, and pause the video. I kind of want you to draw a short little sketch of this and see if you can figure out how many lines of symmetry can you come up with for each of these figures. Okay, so if I look at the first one, this rectangle, I know I can draw a line here, and if I fold it across that line, it would be symmetric. I can draw another one across the rectangle. And then my original thought was, I wonder maybe if I could draw one diagonally, but if we draw it diagonally and you fold it, right, this corner is not going to match up with a similar corner on the other side, right? It's not going to fold perfectly on top of itself like a reflection would. So the most I've gotten here, and unless I'm missing something, is 2. On the triangle, for a second, I didn't think that we could draw any lines of symmetry, right? I can't like fold it in half there and it become the same image. But I think that maybe we can draw a line of symmetry here, but it just depends on if these two sides, and I'll kind of darken those, these two sides are congruent. Because if they are congruent, and some things work out with the angles, it's possible that I could draw a line of symmetry there. So I'm going to say for this one, maybe 1, but it could just be 0. And then for that last shape for the L, and again, I'm kind of working under some assumptions here. Assuming that this L is the same height as it is length, I see one line of symmetry that I could draw, and that's right here across this corner. Because if I fold across that corner, that should fold on top of itself. So that's going to be 1. All right, the other type of symmetry is rotational symmetry. So we've got some definitions down here. It's really exactly what you think it is. It's, can you rotate the figure around a fixed point and it still be symmetric to itself? So could we rotate it, think about like a puzzle piece. Could you turn it and it could still lock in the same place even though it's turned a different direction? So for rotational symmetry, we want to make the note here. Notice that it's a fractional part of 360 because we're dividing, like a full rotation would be 360 degrees. So what they've done here, they say a star has a rotational symmetry of 72 degrees. And if we zoom in on their work here, the reason they're saying that is because a star has 5 points. So if we divide that by 360, we get 72 degrees. Now they've also listed a few other angles of rotation, 72, 144, 216, and 288. All of these are multiples of 72. So for instance, if you rotated this point, or this figure rather, by 144 degrees, that would be like 2 72-degree turns, right? That's how rotational symmetry works. So let's look at a few examples of rotational symmetry. So your directions are pause the video, try to determine whether each figure has rotational symmetry, and if it does, let's try to think about what the angles of rotational symmetry might be for that figure. All All right, so this first figure is a square. So I'm thinking if I put the point of rotation here in the middle and I rotate, I think that there are going to be angles of symmetry, or sorry, of rotation, and that's my daughter, at 90, 180, and 270. 360 will map it back onto itself, but we're looking for things that are less than 360. All right. The triangle, even though it looked like it had symmetry down the middle as far as a line goes, I don't see a place where I can put a point and rotate that. So I'm going to say none. That is not symmetrical rotationally. And then the arrow at the end, if we put our point of rotation here, right here in the middle, I'm going to say that does have an angle of rotation, but the only angle of rotation I see is 180 degrees. I could take this and spin it 180 degrees and it would map onto itself. Whereas on the square, right, if I draw that, 90 degrees would take this corner to that corner. That would just give us kind of one turn. All right, so let's make sure you have those notes taken for tomorrow. Have any figures drawn that you need to, and we'll do some work together in class.